Alright, students, welcome to yet another very exciting lecture in this course, CHM413, titled Analytical Chemistry 2. Recall that this is the fourth lecture in this course. What are the intended lesson outcomes? By the end of this lesson, learners will be able to define and explain some basic conductometry terms, classify substances based on their electrical conductance, distinguish between equivalent and molar conductivity, list and explain those factors that affect the conductance of an electrolyte in solution, and states Rioch's law of independent migration of ions and lists its applications. So students, on your own part, avail yourself, make yourself available for this particular lecture, because you have a lot to benefit by you attending. I also enjoin you to participate actively in the class activities. I remain your facilitator, Dr. Emeka Chima Ogoko. Thank you. Hello, students. Once again, this CHM413 Analytical Chemistry 2. The topic for this very fourth lecture is conductometry methods of analysis. I remain Dr. Emeka C. Ogoko, your facilitator. Intended learning outcome, and earlier we mentioned in the introductory video or slide above. However, by the end of this lesson, learners would have been able to define the basic conductometric terms, classify substances based on the electric properties, distinguish between equivalent and molar conductivity, and list and explain the factors affecting conductance of electrolyte solution, and states law of independent migration of ions. Introduction. This is another type of electroanalytical methods of analysis. Conductometry means measuring the conductivity. Conductometer measures the electrical conductivity of ionic solutions. In other words, conductometer is a device used in measuring electrical conductivity of ions in solution. This is done by applying an electric field between two electrodes while the ions wander this field. The anions, which is the negatively charged ions in solution, migrate to the anode, and the cations, the positively charged ions in solution, migrates to the cathode. In order to avoid substance conversions and the formation of diffusion layers at the electrodes, work is carried out with alternating voltage. The rule of thumb is that the frequency of Conductors are divided into one, metallic or electronic conductors. Metallic or electronic conductors. Metallic or electronic conductors are conductors which conduct the electricity through the electrons. This example of this type of conductors are all metals. All metals are good conductors of both heat and electricity. Graphite is a good conductor of electricity, though it is a non-metal, an allotrope of carbon. In metallic conduction, no chemical reaction occurs during the conduction of electricity, and conductivity decreases with increase in temperature due to vibrational disturbances. So, uh, then the next type of substances we have to look at are the electrolytes. The electrolyte is a substance which, in aqueous solution or molten form, allows electricity to pass through it and is decomposed into oppositely charged ions during the process of electrolytic process. Example or examples of electrolytes are dilute solution of sodium chloride, potassium chloride, and other salts. Uh, and other examples of electrolytes are organic acids like ethanoic acid, methanoic acid. Then acids, dilute acids like dilute HCl, uh, dilute hydrochloric acid, dilute tetraoxosulfuric acid, among others. Free flow of ions towards the oppositely charged electrons occurs, and during conduction of electricity through electrolytes, oxidation occurs at the anode, reduction occurs at the cathode. The conductivity therefore increases with increase in temperature as the extent of ionization increases. The electrolytes undergo dissociation to form ions, either in molten state or in aqueous solutions. The electrolytes are further divided into two basic types on the extent of ionization in water, where we have strong electrolytes, weak electrolytes, and non-electrolytes. So we will consider strong electrolyte first. Strong electrolytes are those substances that undergo complete ionization in water. For instance, sodium chloride, potassium chloride, tetraoxo sulfate, potassium tetraoxo sulfate 6 salts, hydrochloric acid, tetraoxo sulfate 6 acid, sodium hydroxide, sodium nitrate, etc. Then the weak electrolytes are those substances that undergo partial dissociation or ionization in water. Examples are hydrofluoric acid, ethanoic acid, ammonium hydroxide, methanoic acid. Therefore, the last category here, non-electrolytes, these are those substances which do not furnish ions for electrical conduction. Example are urea, glucose, and sucrose. So the equivalent conductance. What is equivalent conductance? Equivalent conductance of the volume of a solution containing one equivalent of an electrolyte is known as equivalent conductivity. The conductance of that volume of a solution containing one equivalent of an electrolyte is appropriately known as equivalent conductivity. It is denoted by inverted V or lambda, where lambda is equals to K times 1000 all over N, where K is the specific conductance, N is the normality, and the units of equivalent conductance is in uh, centimeter square per ohms per equivalence, or meter square Siemens per equivalence. A molar conductance. By molar conductance, what are we referring to? Molar conductance is the conductance of that volume of a solution containing 1 mole of an electrolyte. It is denoted by inverted V M or lambda M, or U. It is related to the specific conductance K as U or mu equal to K multiplied by V, where M is the molarity of the electrolytic solution, K is the specific conductance with units in meter square Siemens per mole. Factors affecting the conductivity of electrolytic solutions. We have temperature. The conductance increases with increase in temperature due to increase in ionization. Then another factor is the nature of electrolytes. Strong electrolytes undergo complete ionization and hence show higher conductivities. The third factor that affects conductivity of electrolytic solutions is the ionic size and mobility. The ionic mobility decreases with increase in its size, and hence conductivity also increases as ionic mobility decreases and size of the ion increases. In molten states, the conductivities of lithium salts are greater than those of cesium salts because of the small size of lithium ion. In aqueous solution, lithium ions with high charge density is heavily hydrated than cesium ion, hence show lower conductivities compared to those of cesium salt. The fourth factor that affects the conductivity of electrolytic solutions is the viscosity. The mobility decreases as the viscosity increases. Hence, the conductivity decreases. As the viscosity increases, the mobility of the ion decreases and the conductivity decreases. Then the last factor, which is also very vital and important, is the concentration. Equivalent conductivity and molar conductance increases with decrease in concentration, since the extent of our ionization increases. Specific conductance K increases with increase in concentration of solutions as the number of ions per unit volume increases. The conductance of that volume of a solution containing 1 mole of an electrolyte is known as molar conductivity, whereas the conductance of that volume of solution containing 1 equivalent of an electrolyte is known as equivalent conductivity. Kirchhoff's law of independent migration of ions. This law states that at infinite dilution, the dissociation of the electrolyte is complete, and hence each ion makes definite contribution to the equivalent conductivity of the electrolyte, irrespective of the nature of other ions associated with it. Therefore, the limiting equivalent conductivity of an electrolyte is the algebraic sum of limiting equivalent conductivities of its constituent ion. Applications of law of independent migrations of ions. It has application in calculation of limiting conductivities of weak electrolytes. Another application is in determination of degree of ionization of weak electrolytes. The degree of ionization of a weak electrolyte at a particular concentration is equivalent to the ratio of actual number of ions formed due to partial ionization to the expected number of ions formed upon complete dissociation. Here, this is the degree of dissociation, which is denoted by an alpha sign, is equals to the ratio of the actual number of ions formed due to partial dissociation all over expected number of particles formed due to complete dissociation. The equilibrium constant to obtain the of the compound. So acetic acid undergoes dissociation, partial dissociation to furnish a solution with acetic ethanoate ion and hydrogen ion. So the equilibrium constant is equals to the concentrations of the forward reaction divided by the concentration of the reactants and the backward reaction. So, the concentration of hydrogen ion is equal to the concentration of the anion at equilibrium. So by the time we substitute these values, the equilibrium constant was obtained as 1.8 times 10 raised to the power minus 5. So this is the end of this instructional video. So thank you for listening. I remain your facilitator, Dr. Emeka Chima Orogo.